Hello, everyone. Welcome. It's great to have you here today. I'm Jennifer Bly with the PyTorch Foundation. A big welcome to our live Q&A on the PyTorch 2.10 release. We're going to start with a short overview of the key updates in 2.10, followed by an open Q&A covering topics such as packaging changes, compiler updates, debugging tools, and upcoming deprecations. I am very pleased to introduce you to our speakers today. We have Andrey Talman, a software engineer at Meta, primarily focused on open source releases for PyTorch and its ecosystem libraries. He works on release management, continuous integration, and process improvements, ensuring high quality and timely delivery of PyTorch-related projects. We also have Nikita Shulga, a software engineer at Meta, where, among other things, Nikita is responsible for PyTorch releases and continuous integration. Nikita is committed to uplifting the developer community and continuously improving PyTorch. We also have Shangdi Yu, a research scientist at Meta, where, among other things, she builds PyTorch compile tooling to improve debuggability and observability. We also have Ashok Imani, a software engineering at Intel on the PyTorch team, focused on performance optimizations and platform enablement for PyTorch on Intel hardware. Welcome, everyone. Thank you to our panelists, and please take it away.
Okay, so I'm gonna give a short introduction, overview of the release. So this release features a number of improvements for performance and numerical debugging. Performance and accuracy has always been a focus of PyTorch releases. This release is composed more than 4,000 commits from 536 contributors since PyTorch 2.9, and thank you for everybody who contributed. So I'll go over migration and compatibility concerns for team currently on PyTorch 2.10 or 2.9. What are the key breaking changes or deprecation they should be aware of when upgrading to 2.10? What are the performance regressions to watch out for the specific workloads? First of all, there's no performance regression. If there are performance regression, please report them to us. Create issue under PyTorch. All BC break-in changes are listed on the release notes. Some of the BC break-in changes are the Onyx exporter changes. Onyx exporter in PyTorch now defaults to the new Dynamo export method and disables fallback for legacy exporters. To use all the fallback behaviors, set fallback true manually. On the release engineering side, we renamed PyTorch Triton, PyTorch Triton Rockham, and PyTorch Triton XPU packages to Triton, Triton Rockham, and Triton XPU packages to make it more aligned with Triton releases. Data loader frontend, we removed unused data source arguments from sampler. This should be no op unless you have a custom sampler that uses argument. In this case, update your custom sampler accordingly. And we deprecated imports from Torchutils data pipe iter grouping that are no longer supported. And the last one is a TorchNN. We removed nested tensor support from TorchNN attention flex attention. In terms of the release matrix for this release 2.10, there's no major changes. We still support Python 3.10, 3.14, with 3.14 being experimental. Stable CUDA 12.6, and CUDA, which is released to PyPy, and experimental CUDA 13. Rockham version 7.1, and this was the biggest change because previous Rockham version was 6.4. And one important note for the next release that is coming up for release 2.11, we're planning on dropping Volta support for the CUDA 12.8 build, and minimum GPU version supported by those builds will be, which is the SM75. And we are doing this mostly because of the Volta support prevents us from upgrading CUDNN for CUDA 12.8 builds. This is some updates. So the next question is Python 3.14 and free threaded support. So I'm passing to Nikita.
Hello. So as you all know, Python 3.14 is the latest stable CPython runtime, and we're excited to announce that it's now fully supported by all the current technologies such as Torch Compile. So you can use Torch compile with Python 3.14 or 3.14t, which is pretty excited if you want to stay on latest and greatest. One thing to note, though, that unfortunately, when we move something forward, we have to slow things down. So TorchScript still doesn't work in 3.14, and TorchScript support has been deprecated going forward. So if you need to use TorchScript, please stay on the Python up to 3.14. But still, TorchScript, the way it was, will be fully supported in this release and 3 upcoming ones. And what else? I think another important performance feature that coming in the 2.10 release is horizontal fusion in Torch compile. Essentially, if you used to have a multiple kernels that have an independent data, they were executed as an individual kernels, but now with a Torch compile, if you have an input like that, you can fuse those kernels together and run the same computation faster. And another performance feature is a very variable length package and support for SDPA that allows you to, again, perform the same SDPA computations that you love for like LLM inference, but you don't need to pad your sequences. You can pack them all together, which results in a faster performance. And obviously, this new operator is fully composable with Torch compile. So if you want to use it in any of the traced graph, you should be able to. And with that, I guess I want to pass it to Shangdi.
Yeah. So in this release, we are introducing some features to help you with ensuring bitwise numeric equivalence, which is increasingly important today because of the MOEs and long RL rollouts. And the first one is the torch.compile will now respect the torch.use deterministic algorithm true API, which means if you turn this on, you get the same execution result from repeated execution of torch.compiled code. And also, we are releasing a new debug mode, which is the torch dispatch mode that record all of the dispatch we do in PyTorch, including operations, the input, output, their hashes, and other metadata like stack traces and other things. So you can look at the log and see where the numerical differences are coming from to debug numerical discrepancies. And we also have a tutorial for this, so you can see more details. And finally, we have tlparse, which is a login tool that has been existing for a while, but hadn't seen too much OSS uses. So we have beefed up a better documentation for it, and we're encouraging people to use it and upload the tlparse artifacts to us when you're reporting bugs, especially for torch.compile bugs. Yeah.
Ashok, do you want to go next?
Yeah, sure. Hi, everyone. In this release, we added several new improvements for Intel GPUs. I just want to highlight a couple of them. As mentioned in the release notes, PyTorch 2.10 expands Intel GPU, XPU, support to the latest Intel Core Ultra Series 3 platform, also known as Panther Lake, for both Windows and Linux, with a smooth and consistent developer experience. We also expanded unit test coverage for Intel GPUs significantly in this release. Another quick thing I want to highlight is the extensibility with SYCL. We added support for implementing custom operators on Windows. So in PyTorch, that means developers can implement custom operators such as domain-specific kernels, fuse stops, or specialized pipelines, and integrate them cleanly using the standard PyTorch extension mechanism. Practically, what that means is you can build custom Intel GPU ops using TorchUtil's CPP extension. We have a very extensive custom SYCL operator tutorial that you can refer towards. So we are excited about these enhancements for Intel GPUs. We hope you take advantage of them. Yeah.
Sounds good. I'll go next. Related to release cadence updates. We published a release cadence for the year 2026. We're thinking about doing 6 releases, 2 releases per month, basically each release 2 months, every 2 months, sorry. And why we're trying to do this, we want to accelerate feature delivery, more frequent releases, basically to allow new features and deliver new features, improvements, and bug fixes for each users faster. So this affects both developers and the companies, and improves responsiveness. The project can respond more quickly to the community about any security issues and evolving hardware and software requirements. Also, this provides us better synchronization. The increased release cadence for the PyTorch every 2 months is designed to better align with the release cycles of key ecosystem projects like VLLM, a popular high-performance inference engine for LLMs. Another thing to note, will variant support. We still support will variant for past release 2.9 and for the release 2.10. It was introduced in the release 2.8 first, and the PEP 817 was just published this week. Please join, and please join the discussion on discusspython.org, and we're looking forward for passing through this PEP and basically incorporating this feature as a stable feature for the PyTorch in the future. And this work has been in progress that the PyTorch team has been working on for the past year. So yeah, this is very important for us.
Basil, do you want to ask some questions from community? Okay, the first question, Reason Note mentions reduced kernel launch overhead with combo kernels, horizontal fusion and torch inductor. Can you explain this, how this works, and what types of models or workloads will see the big improvements? So first of all, there's an API and stable or experimental feature, so you need to opt into that. You can do it by, I don't remember the documentation in front of me, but I think it's like torch inductor config combo kernels equals true. And then you don't need to do anything. When inductor believes that it can fuse the kernels together, it will do so. Why we do it? Because it will yield a bigger performance. Like instead of launching 4 kernels that will execute side by side, unless you launch it in a separate thread, like one after another, unless you launch them in the separate threads, we can fuse 4 reductions together if your GPU is wide enough, and we can provide results faster. It shouldn't have any numerical changes, and it would benefit a lot of workloads. I guess LLM inference would be one of those. Next question, please. So release cadence is increasing to every 2 months. What is the primary motivation for this change, and how do you envision its impacting the development and planning cycles on both? I think the question is, Scott, I don't know, int.
Yeah, I can take on it.
Yeah, go for it.
Yeah, so this is basically to, as I mentioned, to increase delivery time to the user, to basically deliver features faster, any bug fixes faster, and better align with the ecosystem library, so that because, for example, libraries like VLLM, they release every 2 weeks. So for us to be able to upgrade to the latest PyTorch faster, I think this everybody will benefit from that.
Next question, please. The new varlen provides support for rugged and packed sequences. How does this compare to the previous approach for handling variable length sequences, and what is the best practices for migration? I guess the questions are somewhat long, but first of all, I would refer you to look at the release notes. Like I think first couple of questions very closely follow the highlights of the release, and we have a detailed description of what they do, but this is a flavor of flash attention variant where we can have a multiple sequence. We used to pad them and provide like index offsets or like a sequence length. We know that's less efficient because you're wasting memory, and like you need to compute the offsets every time you perform an SDPA, batch SDPA operation. But with a new approach, you don't have to do it, so you can arrive to the same answers faster. But again, please note that this is experimental feature. We might change the APIs in the future, but we advise you to try to onboard on this one and use it. And I guess, as I mentioned in the beginning, that's it's fully composable with Torch compile. Next question, please. Can I run LLMs on Intel iGPU, such as Panther Lake on Windows? And where do I find the best known config installs quantization reference and performance tips? I guess, Ashok, do you want to take this one on?
Yes, thanks, Nikita. So yes, yeah, we support them on. You can run them on latest iGPUs, including Panther Lake Windows, as long as the model fits within the available GPU memory. And you can use torch.compile on Intel GPUs on Windows with auto expression to reduce overhead and improve throughput. For larger models, we recommend using Torchaudio for low precision quantization improvements. We support int4 weight-only quantizations, so models can comfortably fit in the memory available. For the best known configuration and configuration, basically the recipes, best practices, we recommend, first, of course, checking out the Getting Started guide for XPU. We updated that for the latest Windows support for Intel GPUs. You can use the standard APIs like torch.xpu is available to check the XPU device on your system. And also, you can refer to our PyTorch 2.10 blog on AIPC LLM inference playbook, which goes into extensive detail on all the optimizations. We also recently published a flex attention blog on the pytorch.org blog under blogs. You can check that out for latest LLM inference optimizations. And we plan to come up in the next few days with an updated blog for running LLMs on Intel GPUs. So keep an eye out for that. Next question.
Circling back from Mark, so does this mean that I can load an audio file with Torchaudio and generate a spectrogram when using Python 3.14 without any trouble? Yes. If you see any problems, file an issue against Torchaudio, though again, you probably heard about some of the changes to the library. So development of the Torchaudio is kind of getting into maintenance mode, but the media decoding will be handled through the new plugin, which can be transparently used through Torchaudio called Torch Codec, and hopefully that will be sufficient to load the file and generate the spectrogram. But yeah, if you run into any problems, please do not hesitate to create an issue. And I think that implies some sort of a platform support that I might be missing. So I don't know, for example, whether this will work on Windows, on ARM, or something. But in general, if platform is marked as supported, you should be able to do that. Next question, please. Marlies mentions that Torch compile now respect use deterministic mode, and there is a new debug mode for tracking numerical divergence. Can you explain how these features help with debugging numerical discrepancies and ensuring training reproducibility? I think there are two questions shoved into one, so I maybe answer first part and then give a second part to Andy. So essentially, use deterministic mode is something that exists in Eager, where we say that we want to use a specific implementation of the operators, which might be slower, but produce repeatable results by mimicking a sequential nature of the CPUs. We introduce Torch compile will respect this mode and will generate the kernels, fused kernels that will follow the same pattern. So I don't know, if you have a couple of duplicated elements and you're doing something I don't know, top k with index, we will always return the same indices in the ascension order. And Randy, do you want to talk about debug mode?
Yes. So yeah, debug mode is well, as I mentioned a little bit earlier, it's a new TorchScript mode, and what it does is it records all of your operation. It works in both eager as well as in compiled code. So it will record all of your operations, like if you do a sine, cosine, redo, matmul, whatever, and will also record the input and the output. And it uses deterministically hashes the tensors. So when you get a log, let's say if you have 2 runs of some programs, and if you see numerical discrepancies, you can look at the log, which gives you all of the operations and the input output tensor hashes for the 2 runs, and you can compare them to see at which operation exactly does the tensor hash differs, and then you can use that to kind of bisect where your numerical discrepancies comes from. So even though it's a torch dispatch mode, it also supports showing the input and output hashes of inductor generated kernels as well, because we had some special logic added to it. This is a beta feature, so expect API changes, but we've used it to find out a lot of different numerical discrepancies. So we encourage you to use it. And also there's a tutorial for it as well, has a lot of more details. So we encourage you to take a look at that as well.
How do you decide when the fusion hurts latency, memory, debuggability, etc.? And will users get control over fusion policies? I think there are 2 answers to that. A, we run profiling, right? So if you use torch compile with what's it called, maximum search or parameter search, we will try different approach and like benchmark, and whichever approach wins, we will use it in the end. So you will have a higher compilation time, but better confidence about what is available. But also almost all of the fusion techniques are conditioned on some global variables. So if you don't want to do certain things, you can like do torch inductor config something or other. On the other hand, I have to warn you that it doesn't guarantee that like if you opt out of certain fusion techniques, it will not appear in the new releases. So I think this is where like compiler behavior might slightly change from release to release in terms of what fusions we support and which fusions are controlled by which flags. But also, like as Shangdi mentioned, like if you in debug mode, we will probably do fewer of those, and you'll be able to see. And you can always like mark parts of the graph that you don't want to do any fusion, so you don't want to use torch compile. So if you notice that like if fused kernels give you worse performance or worse numerics, you can just like say do not like fuse or whatever, and we will run in so-called compile eager mode when we essentially just trace a graph, but we will call the same operators. Next question, please. Okay, we currently use TorchScript plus libtorch plus CUDA for inference. As we support multiple GPU types in the field, precompiled so files will be cumbersome. Is or will a solution be available where the graph can be exported as is and optimized in the field for a particular GPU at hand? Will this have an API roughly comparable to libtorch? So, yes, so we have AOTI, torch compile AOTI mode when you can generate kernel, and then I also mentioned torch compile eager mode, right? So you can export into AOTI when it essentially traces the graph and just records the operations into a C++ files that will just call into libtorch to execute them, right? So you can try this approach and see how it works for you. But also I would like to maybe say, why do we like, you probably need to understand, like you should start a discussion somewhere about why do you need a C++ runtime, because usually like after we trace the model, the performance of Python runtime versus C++ runtime is very similar. But yeah, like look into the AOTI, and I think that produces not a kernels, but like a generic, like you can just trace your graph and execute it. And also look into ExecuTorch. ExecuTorch is another solution. So ExecuTorch is a stack that we kind of position as something more consumer hardware friendly. So you should be able to export your graph and run it with ExecuTorch runtime, and it will just execute operator by operator. It will not do any fusions. Next question, please. But again, I think it's a great one. Like reach to an issue, so like discussion forums, and let's try to identify the current gaps. Is there any plan for improving MPS support in future versions, or will it stay on the base level as it is? That's a good question. There was some MPS improvements that I think brings an operator parity, but like if you want more, you need to file an issues. But also, like PyTorch is an open source project. We always looking for contributors. We have a tremendous success with MPS backend in terms of community contributions, and we will welcome some. I'd be more than happy to review them and give some feedback. And I think if you notice, if you look at the release notes, we are shifting less to use MPS graph less and use direct metal kernel implementation to make it more compatible and interchangeable with what MLX does. Next question, please. And while we're waiting for the question, oh, great. The release mentions a tlparse tool, which can parse Torch compile logs into easier to view format. Can you briefly introduce the tlparse tool? Shangdi?
All right, cool. So yeah, the tlparse tool, this is not exactly something new. It has been existing for a while, and you've been tuned into the PyTorch podcast. There's actually a podcast about that as well. But we want to advertise it again. To the point where if you are submitting, an issue to PyTorch, especially about torch.compile, we encourage you to look into this tool, and especially if you are not able to provide a repro for whatever reason, this tlparse tool logs will be really, really useful for us developers to, bisect where the problem is and to help you better. And also, if you want to understand what happens inside torch.compile, tlparse also, reveals a lot of the intermediate steps of, what the compiler is doing. So it's helpful in that sense as well. And yeah, if you look at the documentation, there should be an example of, what the tlparse output looks like. And you can pip install it. It's not in the PyTorch repo. It's in the meta PyTorch /tlparse repo. So yeah, check it out and let us know what you think. Next question.
What guarantees does Torch Expert give that the TorchScript failed to give? That's a very good and interesting question. I don't think it does. It's just you need to understand why TorchScript was needed or is needed, and why Torch Expert is better or new solution. Torch Expert is based on a modern tracing mechanism based on the Torch compile. So it uses the same inductor backend to trace through your model. And so everything that could be Torch compiled can be Torch exported. And then you can write your own runtime, such as ExecuTorch, which is more suitable for smaller devices. So I think TorchScript was initially designed with multiple goals in mind, but lately it was used as kind of an inference engine on mobile devices. And as such, we believe ExecuTorch with a static memory plugin is a better alternative. So you can have a smaller runtime. So full TorchScript runtime is pretty large for mobile devices, and especially for embedded devices like, I don't know, watch, glasses, whatnot, whereas ExecuTorch can give you a very, very small runtime. But TorchScript had its uses. I think the challenge is that TorchScript doesn't give you a better performance in general than modern C Python runtimes. And it's somewhat problematic to maintain. And I don't think we've seen a lot of community interest in, we've seen a lot of community interest in using the feature, but we don't see a lot of interest in maintaining that. If you want to help TorchScript project to work somewhere, please do not hesitate to propose some patches. Next question, please. Oh, PEP 817. I think it's a real variant discussion, so I pass the baton to Andrew.
Yeah, thank you, Nikita. Yeah, so basically PIP 817 enables automatic selection of optimized wheel builds based on the system hardware. So it will detect if you're running CUDA on a CUDA version, or NVIDIA GPU, Intel GPU, or AMD GPU, which are currently supported. Instead of the separate indexes, package name, or manual selection, users can just run pip install package, and the right variant will automatically be selected. As I mentioned, the VIL variant PEP 187 was published, and some of our team members, including me, are co-authors of this PEP. And please discuss this on discusspytorch.org. And now we're preparing VIL variant release for release 2.10. It should be available shortly. I will post a note on our PyTorch dev discuss for this. Yes, and I think we're looking forward on continuing this work on PEP 817. I think it's very promising. Next question.
If there are any, please don't be shy. How does Torch compile interact with TorchFX? Does it still generate FX graph, and when should I use FX directly? That's a very good question. I think, yes, it does. Well, depending on your definition of FX graph, if you're talking about like TorchFX subnamespace, maybe not all of the artifacts that Torch compile produces are FX graph, but they semantically always like direct acyclical graphs, so they are FX graphs, and we try to functionalize the code, like not to maintain any internal state. You can use FX graph if you want Torch compile to express something better than it can trace, or if you have something that you notice is not very well traceable, or you notice a graph breaks, you can always like rewrite your code in FX graph fashion to make it more traceable. But I don't think you need to use FX graph directly in many cases. Next question, please. No, looks like we are short of questions. If so, thank you very much for your attention.
Thanks, everyone. We really appreciate you joining us today for our 2.10 live Q&A. A big thank you to each of our panelists. So thanks, Andrey, Nikita, Shangdi, and Ashok. We really appreciate you walking us through the 2.10 release and answering questions. Thanks to everyone who did provide your questions. Be sure to check out the 2.10 release blog, which we can link in the comments. Also, be sure to check out the PyTorch newsletter at pytorch.org/newsletter. Follow us on social media, and then you'll be the first to know about our upcoming live streams and webinars. So thank you, everyone. We'll see you again soon.
I think there was one more question about LocalTensor.
Well, we can go back to it.
Yeah, yeah, great. Thank you very much. So can LocalTensor be utilized by hardware vendors to simulate the behavior of a new collective communication primitive before physical hardware drivers are fully stabilized? That's a very hypothetical question, but yes, it can, but it could be problematic if like you kind of don't have a good idea about what communications you will have and like what latencies. Like LocalTensor is great for seeing how your sharding algorithm will work. I'm not sure if it can be used very well right now to simulate the latencies. Are there any plans to extend LocalTensor to support non-SPMD communication patterns? I'm not very well aware of this one, but like all our LocalTensor and dtensor development happen very much in the open, and I think there is like a regular discussions that are hosted live that anyone can join and ask the team who works on the LocalTensor directly. And I think that was the last question. Thank you again.